Let's address the sizing of a three-phase generator when supplying single-phase loads such as those found in a residential apartment building. The question concerns calculating the appropriate generator size given a set of single-phase loads, specifically 12.8 kV amp air conditioners at 240 volts, 3 2 kV amp electric cookers at 240 volts, and 30-40 volt amp fluorescent fittings at 240 volts. These loads are to be distributed equally across the three phases in neutral of a 415 volts, 240 volts three-phase generator. The initial calculation distributes the loads such that each phase, let's say phase A, phase B, and phase C, carries 4 air conditioners plus 1 electric cooker plus 10 fluorescent fittings. This results in each phase carrying 4 times 0.8 kV amps, which is 3.2 kV amps, plus 1 times 2 kV amps, which is 2 kV amps, plus 10 times 0.04 kV amps, which is 0.4 kV amps. Adding these together, each phase has a total load of 5.6 kV amps. The question then arises, should we use the 5.6 kV amps as the basis for sizing the generator, or the total load of 16.8 kV amps, which is 5.6 kV amps times 3. The correct approach is to use the sum of the loads on each phase as the basis for sizing the generator, which is 16.8 kV amps. Here's why. When distributing single-phase loads on a three-phase generator, the fundamental goal is to balance the load across all phases as much as possible. This balance is essential for the generator's efficient and safe operation. Uneven loading can lead to overheating, reduced efficiency, and potential damage to the generator. By distributing the loads as equally as possible across the phases and neutral, we aim to ensure that each phase carries approximately the same amount of current. In this scenario, we've achieved a balanced configuration with each phase carrying 5.6 kV amps. Although 5.6 kV amps is within the capacity of many single-phase generators, the total demand of the apartment complex is the critical factor. The total load, the summation of all the single-phase loads, is 16.8 kV amps. Therefore, using a three-phase generator with a minimum capacity of 16.8 kV amps is essential. Sizing the generator based only on the single-phase load of 5.6 kV amps per phase would result in an undersized generator. An undersized generator would be unable to handle the total demand, leading to potential overloading, voltage drops, and ultimately, failure of the generator. While it's true that each phase only sees 5.6 kV amps, the generator as a whole must be capable of supplying the sum of all these individual phase loads simultaneously. In summary, while balancing the single-phase loads across the three phases is crucial for efficient operation, the generator must be sized based on the total apparent power demand of all the loads combined, which is 16.8 kV amps in this case.